In this work, we present a novel hybrid rigid-soft continuum manipulator, which integrates high-resolution tactile sensing in a form factor that is forceful, compliant, inherently safe, and easily controllable. We utilize a hybrid approach motivated by scale invariant principles to fuse the rigid and soft design domains while addressing their respective challenges. Within robotics, continuum manipulators have long been an active field of study. By utilizing a serial arrangement of rigid links, a continuum body, or hybrid structure, combined with a selected method of actuation, typically embedded fluids, tendons, smart materials, or electromagnets, high degrees of freedom are achieved in a structure whose constitutive material can be actuated to form curves with continuous tangent vectors. This unique configuration enables a variety of dynamic behaviors and methods of manipulation. Continuum manipulators are often described analogously to biological structures, in particular trunks, tentacles, tails, and tendrils, and biological inspiration is usually cited as the progenitor of their dynamic capabilities. Digging further into this biological inspiration, we see that many biological systems have evolved towards tapered limbs that utilize helical and spiral-like grasp behaviors as methods of manipulation. The tapered structure of these limbs describes a function that scales limb diameter linearly along the length of the limb, resulting in a logarithmic change in stiffness, assuming an approximately isotropic body. This compliance gradient efficiently enhances the distal flexibility of the limb without sacrificing the power of the proximal regions. The result is a limb that is efficiently adaptable to a wide variety of objects and maintains the appropriate amount of power and flexibility necessary regardless of the object size. In effect, the manipulator's grasp behavior is scale invariant. In our manipulator design, we select amongst current approaches of continuum manipulator structure and opt to use a hybrid tendon actuated exoskeleton covered soft continuum layup as the basis of our design. In addition, we utilize a serpentine folded flexure hinge designed to enable compliance within the exoskeleton due to its compact form factor, ability to transmit large forces, and maintain large deformations under elastic loading conditions. These compliant hinges, in contrast to discrete revolute hinges, provide the ability to tune and optimize their compliance behaviors via their geometric parameters. Assuming isotropic material and constant area moment of inertia, a shape similar folded flexure hinge will deform approximately equivalent to an analogous series of revolute hinges, where each notch of the folded flexure hinge acts as a discrete joint actuated by a linear spring. Thus, the minimum energy deformed configuration can be approximated geometrically as a polygon with the same number of sides as there are segments, the compliance of which will be equivalent to a series summation of the spring stiffnesses. Thus, as the number of segments approaches infinity, the folded flexure hinge more closely approximates a circle, while the stiffness profile remains constant along its length. To achieve the aforementioned helical grasp and hence scale invariance, we create a novel variant of the folded flexure hinge, where the cross-sectional area and thus area moment of inertia varies linearly along a shape-similar extrusion profile. The revolute joint approximation of the folded flexure hinge deformation models the deflection of an individual segment of the folded flexure hinge as an isotropic cantilevered beam under the action of a free end load until contact is made with an opposing segment. Thus, the hinge's deflection can be simplified as a revolute joint with a rotation angle equivalent to the summation of the deflection angles of the two opposing segments. Utilizing Euler-Bernoulli beam theory, we find that linearly varying the area moment of inertia and hence the stiffness induces a deflection that varies as the natural log of the distance from the fixed end. When applied in tandem with the revolute joint approximation, we predict that the novel variable area folded flexure hinge will deform approximately logarithmically as a spiral. We demonstrate and validate these predictions using a 3D printed proof-of-concept model. The exoskeleton is designed as a U-shaped half-lumen and integrates two variable area folded flexure hinges in a parallel configuration to maintain out-of-plane stiffnesses. Tendon routing channels are placed running perpendicularly through the variable area folded flexure hinge segments. Additional tendon and camera routing channels are placed running through the exoskeleton's posterior surface. The sensing surface is illuminated in a typical configuration to satisfy the conditions of the photometric stereo method using a flexible PCB lying between the elastomer and the exoskeleton. Using the shown manufacturing process flow, we fabricate the continuum manipulator, which includes elastomer mold design, casting embedded rigid components, and painting the reflective skin. Using the constructed manipulator, we demonstrate the adaptability that this scale invariance design approach enables by grasping irregularly shaped everyday objects. To further demonstrate this scale invariance, we grasp identical tools of varying sizes. We evaluate the forcefulness of our manipulator by measuring the transmitted force and torque through 3 motions: screwing, hammering, and pulling on a variety of handles, and compare its performance to a traditional parallel jaw gripper. We find that overall the Continuum Manipulator is approximately twice as forceful as a parallel jaw gripper. Interestingly, the manipulator can only maintain torques for rotations that follow the direction of its spiral. In the opposite direction, the manipulator will quickly detach from the handle. This is an inversion of the universality that scale-invariant approaches seem to afford, and demonstrate the functional trade-off for taking advantage of scale-invariant behaviors is that they are in fact directional. Finally, we demonstrate the grasping and tactile feedback capabilities of our gripper in tandem using a demo task. Please contact us at the following email addresses for further questions. Thank you.